the way today is going to go is the following. So we've kind of built up most of our preliminaries at this point. So I'm going to start by stating some epsilon regularity theorems for you. I'm going to start off with what sort of the most recent ones. And I mean, so the epsilon regularity theorem we stated yesterday, right? This was the statement that if you have an Einstein manifold, say, and if the ln over 2 bound for the curvature is small, then you actually have to have a bound on the curvature. This was our statement yesterday. And essentially, we sort of declared this was not so useful or interesting because you can't control this. I mean, the point of an epsilon regularity theorem is that this control you assume should be something that you can, in legitimate situations, get out of. So we're going to start today where I'm going to state for you an epsilon regularity theorem, where the assumptions will be, on the one hand, slightly bizarre looking if you're not used to them. But on the other hand, what we're going to see really probably tomorrow with the structure theory of lower reach is that this is a condition that you can legitimately control. So this is all that really counts, is that if you can control this, then we can actually prove regularity theory. Then I'm going to state a simpler epsilon regularity theorem. I mean, one of the original ones going back to Anderson, which still is going to use pretty much all the tools we've built up to this point to prove, and we'll prove it. And then we're going to kind of take a side detour, and we're going to kind of state theorems for a while. I mean, it would have been nice to maybe even do this at the very, very beginning, but I decided to sort of make you slug through some mud first. So I mean, it would be nice to see where all this is heading. All right, what is the regularity theory that people understand for Einstein manifolds? And maybe tomorrow a little bit, what is the structure theory people understand for lower Ricci curvature? So we'll kind of just state some theorems. And then we'll spend the rest of the week sort of picking off little pieces of this and that to prove where the techniques are sort of most useful. So let's start with just some epsilon regularity theorem. So the following, which we will not prove by the end of this week. So this goes back, in fact, this is just maybe about a month old. This goes back to myself and Shiger. So what it says is the following. So let's consider a Riemannian manifold. Maybe assume it's complete. With two conditions. So we need a Ricci curvature bound. Well, let's take this second, sorry. Let's say with the volume, the ball of radius 1 around P being bounded from below by V. Then, so there exists epsilon, depending on just the dimension in this V, such that if the Ricci curvature is bounded from epsilon above. Note this isn't really much of an assumption. I mean, if it was bounded by anything, it just means you look on a sufficiently small ball so that if you blow it up, it becomes bounded by epsilon. It just means that for spaces with Ricci curvature bounded by n-1, say, this only applies to balls that are at least some definite small size. And this is the key point, the Gromov-Hausdorff distance between the ball of radius 2 around your point and the ball of radius 2 of some other space, which I'll specify, is less than epsilon, where y is inside some metric space that looks like Rn minus 3 across a cone. So that is to say that it's close to a space that at least n minus 3 of the dimensions is basically Euclidean space, and the rest of it is just conical. It can be a cone over anything, but it's got that zero symmetry coming from the cone. Then the regularity scale at P, the harmonic radius is bounded from below by 1. So in particular, if M is Einstein, say, then the curvature scale is bounded from below by 1. Okay. So we'll call this a strong epsilon regularity theorem because of the stratification theory that will come tomorrow. We'll actually see that under just a lower Ricci curvature condition, in fact. This condition here, the fact that a ball can be made close to looking like Rn minus 3 across a cone, is something that actually holds true at most points. That this is really what the stratification theory tells you. So let's maybe make another remark. So note, in particular, so say M is Einstein, so under the case where M is Einstein, say, then if what we're saying is that if the ball of radius 2 of your point is Gromov-Hausdorff close to, say, the ball of radius 2 in Rn, right? So it's just saying that in this very weak sense of the word, it looks like a ball in Rn. Right? So it looks like a Euclidean ball in this epsilon sense of the word, right? Then this implies that the curvature is bounded by 1 on the ball of radius 1. So the way you should interpret this is weakly close to Rn implies smoothly close to Rn. That's really kind of the essence of this. This statement here was known before this statement here. The key point, and you'll even see by the end of today why the M minus 3 is important. But the key point was to push it down to that. Okay. So, so this statement as it stands kind of goes back to Anderson and Cheeger and Colding. So instead, what we're going to do today is we're going to prove something a little bit weaker. In fact, we're going to play the usual game where I'm going to make a statement for you. And we're not going to quite prove that. We're going to even prove a slightly simplified form of that. However, at least this simplified form is sort of an illegitimate simplified form in the sense that we're not cheating. I'm saying it this way so that we can avoid a couple of technical things we're going around, but the moral will be the same for what I'm about to say. I mean, there's no sort of legitimate issues that appear in going from one to the other, just basically a point picking that I don't really want to get into. So instead, we're going to focus on the following. So this was somehow the first real epsilon regularity theorems. This goes back to Anderson, which was somehow in this spirit where you're not assuming things like LP control on the curvature. I mean, that this is something that you can't sort of legitimately control. So you want something weaker, something like Gromov-Hausdorff or volume or something that you can actually hope to get some control over off just a completely random solution. So what Anderson proved was the following. Oops, let's make sure I have the right statement here. So there exists epsilon of n, positive, such that if the Ricci curvature of our space is bounded from above by epsilon, so again, this just means you're looking at a small ball if you want, and the volume of the ball of radius 2 around our pointed space is bounded from below by 1 minus epsilon times the volume of the ball of radius 2 in Euclidean space. Then the harmonic radius at P is bounded from below by 1. So let's just think about this statement for a second. So, I mean, just pretend Ricci flat, who really cares? So if this thing is Ricci flat, I mean, you know that the volume of this ball is in fact bounded from above by the volume of the same ball in Euclidean space. That's what the volume ontoticity was that we did at the very beginning of the week, right? So what we're saying is that this ball really has almost maximal volume. It volume-wise is very close to looking like a ball in Euclidean space. And then what happens is the epsilon regularity says is that once you hit that sort of regime, you actually have to, again, be smoothly close to Euclidean space. You actually have to be close to it in a real way. Same deal, by the way, as always, M Einstein implies that we can take the curvature scale instead at our point P to be bigger than or equal to 1. So the curvature on the ball of radius 1 is bounded by 1. Okay, good. So let's almost prove this statement. And I'm going to give you a slightly weakened form that we'll prove, but I'll tell you exactly where it is that we're using this weakening, and it's not in a real manner. There's going to be a point picking that we'll get to avoid by doing this. It's somehow, I think it's a better way of getting a grip on the ideas involved in the proof, and we can throw out as many technical pieces as possible the first time through it. So instead, we'll prove mini theorem. This, I believe, the way I'm about to state it, is proved almost exactly inside Peterson. So there's a nice source for this. So let's let M and G be compact. With Ricci identically equal to 0, say. And there exists epsilon positive, such that if for every point, if for every x inside M, we have that the volume of the ball of radius 2 around x is bounded from below by 1 minus epsilon times the volume in Euclidean space. Then the curvature scale of x is bounded from below by epsilon. So that's just to say the sup over the ball of radius epsilon around x of the curvature is bounded from above by epsilon to the minus 2. Okay, so what's the difference between this and this? Well, for one, I'm assuming Ricci flat. That is really nothing. This means in limits, I'm going to be able to say it's a smooth limit as opposed to having to make a little finagled argument. It lets me work with curvature instead of harmonic radius. That's it. The other statement that looks, it'll look at first glance like it's a real difference, is the fact that I'm assuming for every single point in this space we have this lower bound. That feels like a real assumption. In fact, it is not. The point is that, well, I'll show you exactly where it happens, but basically we're going to want to do a certain minimization process at some stage. This being compact means we can do that. And in this case, we'd have to do a point picking argument instead. It saves on energy. Okay, so let's prove this. So how does one prove a statement like this? Well, the standard trick for this is you do it by contradiction. So we assume it's not true. Just pretend like there is no such epsilon. So what does that really mean? Well, if no such epsilon exists, what that means is that we can find a sequence of Mi and Gi of compact Ricci flat spaces such that on the one hand, the volume of the ball of radius 2 around x for every single point x in Mi is bounded from below by 1 minus epsilon I, the volume in Euclidean space. But there exists some point whose curvature scale of y is less than epsilon I, where epsilon I here is going to 0. Say that explicitly. So if this statement fails, then the point is that for every epsilon, no matter how small we pick it, so in particular we take a sequence of epsilon I going to 0, we can find an example of a compact Riemannian manifold, which is Ricci flat, whose volume at every point is bounded from below by 1 minus epsilon I times the Euclidean volume. But there has to be some point where the regularity scale is really small, less than epsilon I. And that's exactly what it means for this theorem to fail. Great. So now, what's the next trick? So let's let xi be a point inside mi. So we know there's some point whose regularity scale is really small, going to 0. But let's not just pick any point for which that's true. Let's pick the point which is smallest. This is a compact space. This, by the way, is always a Lipschitz function. You can check, even for a general manifold. So let's pick the point xi where this attains a minimum. So such that the regularity scale at xi is equal to the minimum over all x in M of the regularity scale. This line right here is where I'm really using the extra assumptions from here to here. Otherwise, we just use it. There's a point picking that gives you not a minimum, but an almost minimum, something that's close enough to make the next argument work. But good enough for now. Okay, so what do? Well, I mean, let's just call this number Ri. I mean, we know it's going to 0. Whatever it is, it's less than epsilon I. And let's consider a new sequence of spaces, a new sequence of Riemannian manifolds to study. Consider the sequence, well, same mi, but I'm going to change the metric here to be gi tilde, and I'm going to point it at xi. And what I've done here is I'm going to take the metric and rescale by Ri. So that is, I've taken this point where the regularity scale is minimal. I've looked at this ball, where we know on this ball, after we rescale, the curvature is bounded by 1 on this ball. So what I want to do is take that ball of radius Ri and make it a ball of radius 1. And that's what this does here. Right, so I find the point which is worst behaved. I pick that scale where it's worst behaved, and then I rescale it to a ball of radius 1. So let's study some properties of min tilde. I'll stick a tilde on anything when I'm just trying to be very clear about the fact that this is coming from the rescaled space. You know, I mean, these are all diffeomorphic to this. I just want to be clear. We're thinking of this geometrically as this space. So, first property. Well, let's just be clear about this. They're still Ricci flat. I mean, when I take a space and I rescale the metric, Ricci flatness doesn't change. So it's still Ricci flat. The regularity scale. At every point is bounded from below by 1 now on m tilde. So that is, if I take any point inside this space, then on the ball of radius 1, the curvature is bounded by 1. Why do I know that? That was the main point of picking the minimum, right? So I picked the regularity scale to be the smallest possible, so that when I rescale this thing out, that means if the regularity scale had a minimum of Ri before, then after I rescale by r to the I to the minus 2, the regularity scale has a minimum of 1. And this is the scale invariance property. So we have a definitive lower bound on the regularity scale here. The third key property is that the regularity scale at xi, our point in question, is exactly 1. And this will be extremely important down the road, right? So we have this lower bound, and that'll be good enough for a while, but at the very last step of the proof, we're going to care about this. This is the key point of the contradiction argument. And the last statement we have is that if we look at the volume of the ball of radius r around xi, then it's bounded from below by 1 minus epsilon I times the volume in Euclidean space of the ball of radius r. And this is for every r less than or equal to, well, 2 times Ri inverse. So the point is that originally, we'd assumed the ball of radius 2 had this condition, but by volume ontonicity, that meant on the original spaces for all radius less than 2, we still had this condition. But after we blow up, ball of radius 2 became ball of radius 2 Ri. So we actually have on bigger and bigger balls that this actually keeps holding for all radii. Okay, so this is it. These are the key properties we'll need. Okay, so what do we do next? Well, we have a sequence of spaces that have, in particular, a lower Ricci bound. There's one natural thing to do here. At least we pass to a subsequence to force there to be a Gromov-Hausdorff limit. So that's nice. However, we can do better, right? Because these things actually have, so I mean, you can already say that after passing to a subsequence, these things will Gromov-Hausdorff converge. This is just by Gromov compactness to some x dx. But the whole point of what we went through yesterday, in fact, was that so we can now make the following statement. These spaces all have regularity scale bounded from below by 1. So that actually means this guy is a manifold, which we'll just call M. So these guys actually converge to some manifold. And this manifold, the convergence now, because these things are all Einstein, the convergence is actually smooth to this. So that means for every radius, if you go far enough in the sequence, there's actually a diffeomorphism between the ball of radius r around this guy and to this guy. So it's the pullback matrix actually converges smoothly to G. In particular, using this, what can we say about M as a limit space? Well, the convergence is smooth here, so in particular, Ricci flatness is preserved. So it converges to a Ricci flat space. Great. Second condition is that, well, again, since it's smooth convergence, so in particular curvature is converging pointwise, we have that the regularity scale was bounded from below by 1 in all these guys. It is here too. The regularity scale bounded from below by 1 on M. The third condition, well, the regularity scale at this point here was exactly 1. Now let's just think about what that says. That says that on the ball of radius 1, there is a point where the curvature has norm 1. Right? The convergence here is smooth, so that means there's got to be a point in the ball of radius 1 around here where the curvature is actually 1. So that means that the regularity scale at our base point x is exactly 1 also. And our last condition, so all I'm doing is saying is basically all these properties are limiting out. That's all I'm saying right now. Well, again, convergence here is smooth, so in particular, volume is converging on each ball. I mean, this is something you just write in coordinates, and you see the silly thing converges out. So that means that for every r less than infinity, we actually have, well, that the volume of the ball of radius r around x is bounded from below by the volume of the ball of radius r in Euclidean space. Now, I do want to make one interesting statement at this point. This is a Ricci flat space, which means we automatically have the converse. This thing is always bounded from above by the volume in Euclidean space. So that means on this space, we actually have equality. Okay. So what? So we claim there's a contradiction, that you can't have a smooth, complete, Ricci flat space that satisfies all these conditions. Why? Well, let's see what 4 gives us. So remember, sometime in the middle of last week, we said something about 4. Right? So the point was that on any space with non-negative Ricci curvature, we knew that this guy here was a monotone quantity. And we asked the question at some point, what if there exists radii for which this has remained unchanged? So in particular, what if for every radius this thing is a constant? Well, what we said was that implied that M was actually isometric to the cone over some smooth manifold. Whose Ricci curvature was at least n minus 2. This is not really important for what I'm about to say. I'm just reminding us what the exact statement was. But if M is isometric to the cone over some other space, so we were studying cones just yesterday. M is itself a, so what's a cone? A cone is this, right? A cone space in principle is a smooth manifold away from the origin. And what we said was that there's only one way in which the cone space of something can itself be a smooth manifold everywhere, including the origin. So this actually implied automatically that Y is just the standard n minus 1 sphere. So M being smooth plus M being a cone space means that Y's got to be the standard sphere, and that M has to be isometric to Rn. I mean, the cone over Sn minus 1 is just Rn.
Could you argue, I mean, you know that the constant is 1, so can you say immediately that it's Rn?
You actually can say that if you have a smooth space whose volume is that of the sphere, because that's what that really says, and with this lower bound, then it is the sphere. But that's sort of a whole other argument. It was easier just to say, well, it's a smooth space, and you clearly can't be smooth unless you're... Either way will work. You can make that work. I'll say it that way. Okay. I say we're done. Why are we done? Well, condition 3 here was that the regularity scale at x, whatever our point is in Rn, is 1. That is to say, there's a point in the ball of radius 1 around x where the curvature is 1. This thing is flat. That can't happen. Contradiction. Done. Okay. So the moral of this proof's very important. I mean, this sort of contradiction argument for proving estimates, it comes up again and again. You can even prove shadow estimates for the Laplacian through contradiction arguments. I mean, this is a really important technique, especially when you hit nonlinear stuff. The idea being that you want to prove some estimate holds, and so you assume it doesn't, and you end up deriving from this some solution of your equation which has some ridiculous properties that gives you a contradiction. Okay, so hard stuff's over for the day. So I think maybe what will be fun to do for a few minutes, we've got half an hour, we can at least do a deal of this. Let's talk today about the regularity theory of Einstein manifolds. Or just of bounded Ricci. Doesn't matter. And tomorrow, what we'll talk about is the structure theory of spaces with lower Ricci curvature. And what we'll see is how if you combine the structure theory of lower Ricci curvature with the epsilon regularity theorem stated at the beginning today, you'll end up getting this. So I mean, this is sort of a very common way of trying to prove things. Okay, so let's just state theorems. So that is, let's start with something sort of ineffective that just sort of gives us a feel. So when we keep talking about wanting to study spaces with lower or bounded Ricci curvature or Einstein manifolds, whatever, and passing them to some Gromov-Hausdorff limit x, and saying this x can't be an arbitrary metric space. It should have all kinds of special structure. But we've really said nothing so far about what that special structure is. So the best you can say, at the moment anyway, is the following. So this goes back to myself and Chigger. So it says, let's consider some sequence of Riemannian manifolds. MIGI. Let's say they're pointed, whatever. PI. Helmholtz and Gromov-Hausdorff converge to something. Where the Ricci of the MI is bounded by something. I don't really care what that something is. Let's just say m minus 1. If it's A, you can always just rescale these silly things to make it m minus 1. It doesn't matter. And, now the key point, the volume. This is a non-collapsing sequence. It's bounded from below. So what you're going to find in this study for either lower Ricci or bounded Ricci is that lower bounds on the volume sort of behave as upper bounds on the energy. So that is log volume, which actually has at least at one point been literally defined as being the entropy of your space. It behaves as an energy. So you can say more under this condition than you can when these things collapse. Like what I'm about to say is simply wrong without this condition. It also turns out that like on moduli spaces of these things, volume's constant. So this is a reasonable assumption to actually make when you're studying things. then what? Then there exists a closed subset S of x inside X, called the singular set, whose dimension is less than or equal to n minus 4. Dimension here, I mean, it's not a geometric measure theory class, but I mean, it can mean Hausdorff dimension, it can mean Minkowski dimension, it can basically mean whatever notion of dimension you actually care about. Such that the regular set, which is by definition just everything else, is a smooth manifold. So a priori, what we've been doing up to this stage is just sort of saying that, well, I mean, the lower bound here on the Ricci means you can take to some Gromov-Hausdorff limit. We don't know much about what these metric spaces look like a priori. They're just kind of random metric spaces. But now what we're saying is that there's some set which is quite small. Its dimension is very small compared to that of X, such that if you throw it out, everything else is actually a smooth manifold at this stage. So let's make a couple notes. So dimension is in the Hausdorff or Minkowski sense. If you don't know what that means, don't worry about it. All I'll basically say is that this is stronger than this.
Sorry.
Yes?
If the dimension is negative, do you say the set is empty, or?
It won't be. Yeah. I mean, it'll just be zero. I mean, it'll be empty, right?
Yeah.
You can call that zero if you want. Certainly, it's legitimately less than or equal to zero. But yeah. So I mean, morally, the dimension is what you imagine, right? I mean, if it's the dimension is zero, it's a whole bunch of points. If the dimension is one, it's a whole bunch of lines with maybe some points too, so forth and so on. The point being that this dimension actually more corresponds to that intuition than this dimension, but whatever. This is sharp. So there are definitely examples of limit spaces where you have singular sets of dimension n minus 4. Right? So it's not like you're just sort of missing the analysis on these guys, that this can't happen. So, e.g., take R4, mod out by z sub 2. So z sub 2 is just multiplying by minus 1 everything. So it flips it, right? So it's got an isolated singularity. So that this is an orbifold with an isolated singularity. And that this is a legitimate limit in this process. In fact, things that it's a limit of are called the Gucci-Hansen metrics. They're somehow the best sort of example of the simplest Ricci flat example, which is somehow non-trivial. So not a torus. So not flat. So it's a 4-dimensional example, and they limit to something with an isolated singularity.
Sorry, it's a limit of what?
What's that?
It's a limit of what spaces?
Yeah, I mean, I wasn't figuring. I mean, they're called the Gucci-Hansen. Yeah, just the name of the guys who invented them. That's it. I mean, this is they're Ricci flat spaces on what is topologically the tangent bundle of the 2-sphere. And essentially, I mean, it's complete. It goes off to infinity. And if you actually start scaling down to look at what you call the asymptotic cone, you get this. You call these things ALE spaces. This is somehow this is as easy as Ricci flat gets without being flat. It'd be worth writing down that metric explicitly to study it, but I don't remember it offhand. Okay, so this is somehow the ineffective version of a regularity theory. So that is to say, it's saying something about the limit spaces. It's saying that they're regular away from some set. It would be nice to have an effective version of this. That is something that just says that you're handed some sort of space with bounded Ricci or Einstein or whatever, and you're told that it's got a lower volume bound, then what do you know about it? So that is to say, what do you want from, I mean, you're studying nonlinear PDEs or linear PDEs. Heck, what do you want from the theory? You want to know that solutions have C10 bounds, LP bounds. They have a Schauder theory associated to them. So what you want is something similar in this context here. So that is, there should be something you know about the MIs that sort of just give you this for free. So the effective version of this statement is the following. So it says, take some Riemannian manifold, complete as usual, but just one now. Because Ricci's bounded by something, let's just say m minus 1, whatever. And the volume of the ball of radius 1 is bounded from below by V. Then, for every q less than 2, there exists a constant, depending on just n, v, and q, but nothing else, such that we have for free the following. Such that the integral, or the average if you want, over the ball of radius 1 of the curvature to the power of q is bounded. So what I'm saying is that if you have an Einstein manifold, or bounded Ricci, whatever, and then you automatically have an a priori bound on LQ norms of the curvature for every q less than 2, anyway. So you can think of this as a nonlinear sort of Schauder theory for these things. It's sort of an a priori estimate. I mean, we won't really get into it, but what I'll say is that this is actually quite a bit harder to prove than this. This is sort of the combination of two things, but we'll sort of discuss it. That this will be a combination of the stratification theory and epsilon regularity theorems, and this will be a combination of quantitative stratification theory and epsilon regularity theorems. We'll study tomorrow what the difference is. Likewise, let's state a very similar result that's somehow actually much, much stronger. So, much stronger. For every epsilon bigger than 0, there exists some C epsilon of NV epsilon such that the following holds. I should actually point out that just by sort of doing the right limiting process with the next statement, actually, it would be difficult with this one. These statements hold not just for some smooth space, but for the limits, too. I mean, we could have assumed X here was a limit of spaces with bounded Ricci curvature, and the same conclusions hold. And what we have is that the volume, and I'll explain this, of the ball of radius r around the set of points x, such that the harmonic radius of x is less than or equal to r, is less than or equal to Rc times r to the 4 minus epsilon. Okay, so let's try to understand this statement a little bit. So first off, I mean, just pretend like this. If these were Einstein, we can replace harmonic radius with curvature scale if you prefer, whatever. So if we apply this to a limit space, imagine we take m, which is perfectly legitimate. We can. Imagine m here as the limit, so it's x over here, right? Then what do we know? Then these are the set of points. Then, I mean, our singular set is certainly contained inside the set of points where the harmonic radius or the regularity scale, whatever, is less than or equal to r. Because these are exactly the points where it's 0. I mean, these are the set of points where there is no neighborhood that actually has a nice coordinate chart. That's sort of what singular set means. So this set here is somehow the points that are not just singular, but they aren't very regular, right? So that's what, I mean, this is what makes this effective, is that we're going to estimate the set of points which don't have enough regularity. I was like, the regularity is so bad that we're just going to throw them inside the singular set and say they're nasty too. So then, in particular, what this immediately implies here, right, is that the volume of the ball of radius r around the singular set, just by using this inequality here, intersected with some compact subset, say the ball of radius 1, is less than or equal to c times r to the 4 minus epsilon. So what we're really saying here is that this set isn't just four-dimensional. This statement here is really sort of the effective version of saying this is Minkowski dimension 4. It's saying that, so imagine we had a nice smooth manifold, whatever. And imagine living inside of it, you had some nice smooth codimension 4 submanifold. Then you could ask, well, what's the volume of the ball of radius r around this submanifold look like? How does it behave? And it behaves like r to the 4th is the point. Right? So what we're saying is that this up to any epsilon behaves like a codimension 4 submanifold. And really, this is really what Minkowski dimension is all about here. It's saying that not only is this set small, but tubes around the set are small. Especially if you don't know Hausdorff and Minkowski dimension, it's probably better to ignore my next statement. It'll cause confusion. But the point is that you could, for instance, have a set that is like the rationals in Rn. That this has Hausdorff dimension 0, but if I looked at the ball of radius r around it for any r, it's everything, right? So it has Hausdorff dimension 0, but not Minkowski dimension 0. The point is that this is stopping singular set from being too densely distributed. So what this really says here is that not only is the singular set small in some sense, but if you move away from it, you have definite regularity because you're not in this set anymore. That's the moral of this statement. Okay. Well, we have 10 minutes. Let's state 2 more theorems. I told you, the rest of today is pretty just sort of not careful. We just want to see where things are going. And we'll creep our way up to proving as much of it as possible. I think if we're lucky, what we'll be able to do is we'll be able to prove these theorems given the epsilon regularity theorem that was stated at the beginning of today. So tomorrow I'm hoping that we'll state and maybe even prove the stratification theory. And then we'll see if we combine that with the epsilon regularity theorem, we'll prove carefully how to actually get this. So that way we can have at least a complete picture of how this should go, minus the epsilon regularity theorem proof. Okay, so what else? Just to get a feel for what else might be sayable. So I mean, this is not the whole picture, right? So in some sense, these theorems have kind of become semi-sharp in the sense of the regular set. But there's still a singular set here. And we've said really nothing except size about it. We've said it's small in size, and that's nice. That's a nice start. But we'd like to understand maybe more carefully what the singular set can look like and what its behavior is. And in general, this is unknown right now. I mean, there are not a lot of good theorems about this. But there is at least one context in which we do have good theorems now, and that's in the dimension 4 case. So in the dimension 4 case, we can say exactly what these things look like. So let's start by just sort of improving the first theorem there in the dimension 4 case. So theorem. So let's let M4 GIPI converge to something with Ricci curvature bounded. I don't care by what, let's say n minus 1, and the volume. So the same assumption as always. Then X is a Riemannian orbifold. with isolated singularities. So it doesn't have to be a manifold, but in some sense, when you're doing this whole business, if you're to ask, what's the next best thing? If it can't be a manifold, what's the next best thing to a manifold? The next best thing is a Riemannian orbifold. Because what it means is that although it may not be a manifold, a Riemannian manifold, it does mean that locally it looks like that over there. There's always some finite lift of it, such that you're now on R4 with an actual metric, which induces some distance, and you're just a finite quotient of that. So it's as close to being a manifold as you would like without actually being one. It's the next worst thing. So this is the worst thing that can happen. And for bounded Ricci, it would be C1 alpha Riemannian orbifold. If they're Einstein, they'd be smooth. So there are actually applications of this that you can use. So, it's actually sort of, I'm going to call it a corollary, but in truth, you prove this first, and then you actually prove that, is how the proof actually goes. But so the effective version over there can be improved to say the following. So if we have a four-dimensional space with bounded Ricci, and a lower volume bound, then there exists some constant depending on, there's no dimension here, just V, such that the L2 norm of the curvature is actually bounded by C. So what we said was that in any dimension, we could bound LQ for every Q less than 2. And dimension 4, you can actually get 2 out of it. And it's wrong to go higher. I mean, it's 2 plus epsilon is not true ever in general. So this is certainly a sharp result. And we conjecture this is true in all dimensions, the 2. But I mean, that this seems to be this is still open. And likewise, this thing behaves like a codimension 4 manifold in a much better sense. So there's no epsilon anymore. So maybe since we've got 5 minutes, I've actually just got one more theorem to state anyway, so that's good timing. So, I guess my n minus 1 here really is 3, right? That's dimension 4. So again, I want to sort of point out the following, by the way. So that this theorem here about being a Riemannian orbifold, this was understood in the 80s if you made more assumptions on the MI. If you assumed that they had, say, bounded diameter and bounded topology, this was understood. So somehow the point is that, I mean, there's a Gauss-Bonnet that tells you if you have bounded topology, you actually get for free the L2 bound, and when you have the L2 bound, you can kind of go up to here. So in fact, the key point here in actually proving this, well, it was to prove this, and to prove this, the key point is actually the next thing here. So this is actually the bottom of the totem pole here, though. So the idea is you want to see you don't, I mean, topology bounds are for free. So let's consider the following class. So let's let M, I don't care. I'll do it in a compact sense, but there's a local version of this that's true as well. Let's consider the collection of 4 manifolds such that the Ricci is bounded by 3 again. The diameter is bounded above by D, and the volume of the space is bounded from below by V, say. Then there exists some constants depending on just the V and the D, such that MVD has at most C diffeomorphism classes. So the point is, if you looked at the collection of all Riemannian manifolds for which the Ricci, the diameter, and the volume are bounded, there can be lots of such Riemannian manifolds, of course, but there can't be a lot of smooth structures on this. There's at most a finite number of diffeomorphic spaces that can actually have such a guy. So the ordering of the proof of all this actually is that you do, in fact, prove this first in any dimension, then you prove this in any dimension. You use this to prove this in dimension 4, use this to prove this in dimension 4, and use that to prove that in dimension 4. So that's the actual ordering of things. Okay, I'm done. Tomorrow's structure theory for lower Ricci spaces.